This is an example of a problem where we'll need to use the chain rule to differentiate it. The chain rule uses a substitution, so the first thing we've got to do is to identify the inner function. So in this case we could use this as the inner function. So we're going to say let u equal 2x plus 1. If we make that substitution, it means that we can express the original function in terms of u. So it's going to be u to the power of 4. All we've got to do now is differentiate the two parts that we've got here. So if we differentiate u with respect to x, we'll get 2. And if we differentiate y, and the variable this time is u, so apply the power rule, we're going to get 4u to the power 3. The chain rule says that the gradient dy dx is just dy du multiplied by du dx. So we take these two parts that we differentiated and we combine them. So in this case we're going to get 4u to the power of 3 multiplied by 2. So that's going to give us 8u to the power of 3. The final step is to change back to the original variable, which in this case is x. So instead of u, we're going to write that as, well, here's u here, so it's 2x plus 1 to the power of 3. And that's the gradient. This is another example of a function that we can differentiate using the chain rule. So the first thing we're going to do is identify the inner function. So in this case, if we look at that part, that would be a good part of the function to substitute. So we'll say let u equal x squared plus pi over 4. That means we can write the original function as cos of u. So now we've got to differentiate each of these parts. So differentiating the first one with respect to x, well, differentiate that will give us 2x. Pi over 4 is just a constant, so it will disappear upon differentiation. Differentiate the second function with respect to u. The derivative of cosine is negative sine, so it's going to be negative sine u. And then the chain rule says we combine them by multiplying them together. So in this case it will be this multiplied by this. So we could write that as minus 2x sine u. And then finally we change back to the original variable. So it's going to be minus 2x sine, and it will be x squared plus pi over 4. In these examples, it should be obvious that our final result comes from multiplying two things together here. So compared to the original function, the 2x part comes from differentiating the inner function. This part comes from differentiating the outer function, the cos of whatever it is. So it means there's a quick way of doing these problems if we don't want to write down all of the u and the dy du and all the rest of it. Okay, some more examples of functions where we could use the chain rule very quickly. So we look at the inner function and the outer function and we differentiate them and multiply them together. So the first one, if we want to find out dy dx, the outer function differentiated will be cosine of 3x. Okay, so it's going to be cosine 3x, and we multiply by the derivative of the inner function, so it's just going to be 3. So that's our solution there. If we look at this one, the outer function is e to the x, e to the power of something. The inner function is the 5x. So when we differentiate e to the x, in this case e to the something x, we're going to get e to the something x again. We multiply by the derivative of the inner function, which is 5. So that's our gradient. Similar again, so we know when we differentiate e to the something x, we get e to the something x again. but we multiply by the derivative of the inner function. So differentiating that gives me minus 2. So the solution is there. For the final one, if we want the gradient of this one, the outer function is tan. When we differentiate tan, we get sec squared. So it's going to be sec squared half x. When we differentiate the inner function, we're just going to get a half. So that gives us the gradient there.